Discussion of equilibrium calculations from 13.5B and 13.6. As I mentioned at the end of the previous video, I decided to split this up into two because they're pretty long. So in this second part of this particular set of videos, I'm going to show you examples of what I define as the harder equilibrium calculation problems. Again, not really hard, but just trying to solve a different thing. So in these problems, of which I'll do a few examples, you are given all of the initial concentrations of reactants and or products and the numerical value of K, and you are trying to solve for all equilibrium concentrations. So in this first problem, we are forming gaseous hydrogen fluoride from its elements. We're given the value of K, 115, and we are given the fact that we're starting with 3 moles of each component in a 1.500 liter flask, and we're letting it reach equilibrium, and our goal is to calculate all equilibrium concentrations. So I'll begin by writing out the equation, H2 gas plus F2 gas in equilibrium with 2HF. And I'll write out the K expression. K is equal to the concentration of HF squared divided by the concentration of H2 times the concentration of F2. Okay. Our initial concentrations are all the same, so we're starting with 3.00 moles of each in a 1.500 liter flask, or 2.000 molar. Now, normally we would calculate Q to determine whether we have to shift towards the products or reactants in order to achieve equilibrium. That's important. But if our concentrations are all equal, when we plug them into the K expression, we'll see we'll simply get a value of 1. Clearly, K is less than 1, which means we're going to need to shift to the products. Okay? Now, for these types of problems, the ICE table is really essential. So I'll set up my ICE table. My initial molarities are all 2.00 molar. My change in concentration, I'll define my decrease in concentrations of H2 and F2 as minus x, and my increase in concentration of HF is 2x. So my equilibrium concentrations will be 2.00 minus x, 2.00 minus x, and 2.00 plus 2x. Okay? Now, here's what I'm going to do. I am going to take the values in the E column in the ICE table, and I'm going to plug them into the K expression. So my equilibrium concentration of HF is 2.000 plus 2x squared divided by 2.000 minus x times 2.000 minus x, which is equal to 115. Now, if you look at that K expression very carefully, you will see something very important, and that is that the K expression is a perfect square. It's 2 plus 2x squared in the numerator, 2 minus x in the denominator, so I can simplify this, avoid having to solve the quadratic equation to isolate x, and simply take the square root of both sides. So that gives me now, I'm going to leave off sig figs for the time being for simplicity, but we'll come back to them later. 2 plus 2x over 2 minus x equals the square root of 115. Now I simply have a linear equation, and the algebra is easy to solve. I'm going to, in the interest of time, not solve that, but ask you to pause, brush up your Algebra 1 or Algebra 2 skills, and make sure you can rearrange that algebraically to solve for x. When you do, you will find x is equal to 1.528, and it has a unit of moles per liter. Okay? So now I can come back up to my ICE table, and I can actually calculate these equilibrium concentrations. Okay? So this becomes 2.000 minus 1.528, or 0.472 molar hydrogen. Same for fluorine, minus 1.528 equals 0.472 molar fluorine. And my equilibrium concentration of HF is 2 plus 2 times 1.528 equals 5.056 molar HF. Okay? So we've solved the problem. We've calculated the equilibrium concentrations of all species, starting with given initial concentrations in K. Now, you may think you're done, but in these types of harder problems, where you are calculating the final equilibrium position, you must do something very important to check your work. What is that? Well, obviously, you're going to take those quantities, plug them back into the k expression, and make darn sure that the number you get is equal to k, or at least close by sig figs. So to check, I'm going to do 5.056 molar HF squared divided by 0.472 molar H2 times 0.47 molar F2 gives me a value of 115. Great, I solved the problem. So after you've set up your ice table, after you've completed the E column in which you have expressed the equilibrium concentrations in terms of this variable x and plugged it into the k expression, if that expression is a perfect square, simplify the math by simply taking the square root of both sides. Here's our next. So here's the general procedure. Write and balance the equation, write the k expression, list the initial concentrations, calculate Q if necessary, determine the direction of shift. Remember, if there is 0 moles per liter of either reactant or product, the reaction must shift toward that because it can't shift away from it. Define the change needed to reach equilibrium. Write the expressions for the equilibrium concentrations in terms of x in the ice table. Take those expressions from the E column in the ice table, substitute them into the K expression, and then, after that, the chemistry is over. All that's left is math, and all you're really trying to do is use whatever algebraic technique you need to solve for x. Calculate the equilibrium concentrations, and then check by plugging in. We'll do a couple more examples. Here's a challenging one. HI is synthesized from its elements, and the equilibrium constant is 1.00 times 10 to the second. We are given our initial partial pressures of components, and we are asked to calculate the equilibrium partial pressures. So we'll begin by writing out the equation. H2 gas plus I2 gas in equilibrium with 2HI. My Kp expression, since we are given Kp, is equal to the partial pressure of hydrogen iodide squared divided by the partial pressure of hydrogen times the partial pressure of iodine. In this case, I can't really look at the values off the top of my head and determine whether Q is greater than or less than K, so we're going to have to calculate it. So Q is equal to the partial pressure of HI, 0.5 squared, divided by the partial pressure of H2.01 times the partial pressure of I2.005 is equal to 5,000, which is greater than K. K, we're told, has a value of 100. So that means we're going to have to shift to reactants as the equation is written. Remember, the numerical value of K, 100, corresponds with the way in which we've written both the chemical equation and the equilibrium expression. So jump to my ice table. H2, I2, HI, ICE, 0.01, 0.005, 0.5. Because we determined that the system must shift towards reactants in order to achieve equilibrium, that means the change in partial pressures of hydrogen and iodine will be positive. The change in partial pressure of HI will be negative because we're shifting towards the reactants as we have it written. So I'll call this plus x minus 2x. So my E equilibrium are 0.01 plus x, 0.005 plus x, and 0.5 minus 2x. Okay, so the next step, I will take these equilibrium partial pressures and plug them into the Kp expression. Kp equals 0.5 minus 2x quantity squared divided by 0.01 plus x times 0.005 plus x equals 100 points. Now, because our initial partial pressures of hydrogen and iodine were not equal to each other, this is not a perfect square, and we can't simplify the algebra simply by taking the square root of both sides. So what you must do is either use the quadratic formula, or there is an online polynomial equation solver, which I will show you about. Or if you know how to use your graphing calculator to solve for the roots of a polynomial, you can do that as well. Whichever calculation technique works best for you is perfectly fine. And when you solve for this, you find that you have two values of x. X is equal to negative 0.0719, but it is also equal to 0.0355. Now, what does that mean that you have two solutions to x, as you would expect for this particular quadratic? Well, it means mathematically there are two solutions to the problem, but only one of them can be chemically relevant. Because we said x is the increase in partial pressures of H2 and I2, x must be a positive quantity, so we are going to ignore the negative 1 and use 0.0355 as our solution. Now we go back to the ice table and we use our solved value of x to calculate the equilibrium partial pressures. So 0.01 plus 0.0355 equals 0.0455 atmospheres of hydrogen. 0.005 plus 0.0355 equals 0.0405 atmospheres of iodine. And 0.5 minus 2 times 0.0355 equals 0.429 atmospheres of HI. So there is our solution to this problem, the equilibrium partial pressures of all components. But once again, we're not going to stop here. We're going to check by plugging these into the Kp expression, and we get 0.429 squared over 0.0455 times 0.0405 is equal to, on my calculator, 99.9. Which, to my mind, is close enough to 100. Check, we have solved it. Okay, let's do one more example. And this is a very important type of problem because we're going to be seeing this in the next couple of units. At a particular temperature, K is equal to 4.0 times 10 to the negative 7 for this reaction. We're starting with N2O4, and we're going to calculate the equilibrium concentrations of both products when it reaches equilibrium. Okay, so we're going to start, as always, by writing out the K expression. K is equal to the concentration of NO2 squared divided by the concentration of N2O4, which is equal to 4.0 times 10 to the negative 7th. I'll set up my ice table. N2O4, NO2. My initial concentration of N2O4 is 0.10. My initial concentration of NO2 is 0. We don't need to calculate Q because we know if the initial concentration of NO2 is 0, it has to shift in the forward direction in order to achieve equilibrium. So I'll call my decrease in concentration of N2O4 minus x, my increase in concentration of NO2 plus 2x. So my equilibrium expressions are 0.10 minus x and 2x. I will plug these into the K expression. K is equal to 2x quantity squared over 0.10 minus x equals 4.0 times 10 to the negative 7th. Now, at this point, you may think that you must cross-multiply, collect terms, and solve a quadratic equation, or use a polynomial solver, but in this case, you don't need to. Pay close attention. When K is very, very small, that means that, in this case, the shift towards the products is going to be really, really, really tiny. Not 0, but very tiny. We are going to make the assumption that because the equilibrium constant is so minuscule, that the decrease in concentration of N2O4, that is x, is negligible in comparison with 0.10, meaning it is so small that to sig figs, 0.10 minus x is essentially equal to 0.10. So we will make the simplifying approximation by simply canceling x in the denominator. Okay? And what that gives us then is now a much simpler equation to solve. That gives us 4x squared equals 4.0 times 10 to the negative 7th times 0.10, or x is equal to 4.0 times 10 to the negative 8th divided by 4 square root, or 1.0 times 10 to the negative 4 molar equals x. And now we see if we take 0.10 in the new denominator of the K expression and subtract 0.0001, we just get 0.10. Okay? So now we can go back and we can calculate our equilibrium concentrations. 0.10 minus 1.0 times 10 to the negative 4th is simply equal to 0.10 molar N2O4. x is small, but it's not 0. So 2 times 1.0 times 10 to the negative fourth equals 2.0 times 10 to the negative fourth molar NO2. And there are our equilibrium concentrations. Okay? Once again, we'll check. We will do concentration of NO2, 2.0 times 10 to the negative fourth squared, divided by the concentration of N2O4, 0.10, and that gives us 4.0 times 10 to the negative 7, which is exactly equal to K. Okay? So, to summarize, there are 3 mathematical techniques that we're going to use to solve these, quote, harder equilibrium calculations. Okay? If you write out your K expression, and you see that it is some concentration to some power times some other concentration to some power, in other words, the K expression is a perfect square, you're going to simplify the algebra by simply taking the square root of both sides. If the K expression gives a quadratic equation, then you are simply going to use the quadratic formula or some other calculation device. And finally, if K is very, very small, generally on the order of 10 to the negative fifth or less, you are going to use what I like to call the simplifying approximation. And that is simply going to be to cancel x when it is being added to or subtracted from a much larger number. Okay, that's pretty much it for this section. And in our final video on Chapter 13, we will talk about Le Chatelier's principle.